Thank you very much. So, and in particular, we are deeply appreciate the possibility that we can continue our scientific activity in Kharkiv and realize initiatives such as Kharkiv Quantum Seminar. And today, I'm very happy to introduce our today's speaker, Dr. Junghyun or Paul Lee. He has been a senior researcher at the Center for Quantum Technology at the Korea Institute of Science and Technology, KIST, since 2022. Prior to his role, he served as a postdoctoral researcher at KIST, where he began his work on developing defect qubit-based quantum technologies. He received his Bachelor of Science in Physics and Mathematics from the University of Chicago and his PhD in Physics from the Massachusetts Institute of Technology. His broad research interests include quantum information processing using defect qubits in solid-state materials, spanning topics from material science to device engineering. His today's talk is devoted to this fascinating topic towards quantum-enhanced sensing using solid-state spin defects. Please, Junghyun, the floor is yours.
Thank you, Andre, for nice introduction. And I feel really honored to be invited for this prestigious quantum seminar series held in Kharkiv. So my name is Paul. So I will today talk about some of the exciting and interesting research going on in Korea. So many of you already are very familiar with the how the quantum technology is evolving. It's evolving really fast, and people are already thinking about some practicality of this quantum technology towards the more of the quantum enhanced measurement using some quantum mechanical nature. So in metrology, in quantum simulation, and quantum computing, many of us already heard amazing news every year coming out from different companies or some research group. They're achieving some quantum enhancements and quantum supremacy, especially shown in quantum computing. It's a very exciting moment for everyone. So I want to start with the famous quotation from Professor Sid Lloyd at MIT, where he said, quantum mechanical enhancement is like a it's like a symphony. It's basically not a solo voice. It's a symphony of different voices. And this actually makes it interfere to each other and then make it, sound beautiful. So basically using this quantum mechanical interference, people already demonstrated some interesting quantum algorithms using small size quantum machines already like 30 years ago. So using the NMR machine, they already show that you can use a nuclear spins as a quantum bits and encode some information and then do very basic quantum algorithm. So this field of quantum technology, which has been very fastly evolving these days, but started already like 30 years ago. And at the time, the limitation was about the scalability and very noisy hardware platform with the slow gate operation. So a lot of things were very troublesome. But nowadays, because of the technological advancement, now people can observe more clean quantum mechanical behaviors and now more controllable, manageable way to control these quantum phenomena. So some of the interesting advancements are done in laser control system, where now you can make a very narrow line with lasers, and also high power, low power, very fast pulse lasers to do some very precise optical control. And also because of the development of the semiconducting nanofabrication techniques, now one can make a very nice chip-based quantum devices, for example, like superconducting qubit devices or ion trap on a chip. So these allowed for more of a precise electric control. And also in terms of the measurement side, now we can detect a single photon level and even like a number resolving photon detectors to actually have more high efficiency measurements. And in quantum systems, is it really important to have a very high efficiency measurement? Because it is a very the measurement, it is a very critical procedure in quantum mechanics. So advanced detectors really helped to understand and acquire more of a pure quantum information from these quantum systems. And nevertheless, having these vacuum systems and low temperature system with a very simple just button click allowed people to, to get more involved in this in the field, because now you can just buy these off the table, and then now you can just set it up and then just do the measurement automatically. So all these advancements really allowed us to now access the more of advanced quantum mechanical nature, and then now it allows us to have more of a application of these quantum technology. So there are lots of platforms you can play with to deploy these quantum protocols, quantum mechanical protocols. From the atom trap side, you can use the cold atoms and optical lattices, or Rydberg atoms, or ion traps. So these are the famous platforms where you optically trap them or electrically trap these single atoms, which act as a qubit, and make some quantum machines out of it. And the lower three are the solid state system-based quantum platforms, where you can use the quantum dots, the spins of quantum dots, or charge of quantum dots to encode the information, or superconducting qubit, which is the artificial atom that you can make from the very basic electric circuit structure. And also, we have the atomic defects in solid state materials, usually or wide bandgap materials. So today I'll be more focused on these defect qubits in solid state materials. So these systems have naturally trapped atoms, so you don't need to trap these. So it's already trapped inside of the solid state lattice. So you can make it from the singles to multiple spins in a host material. So it is a very simple system. So you don't require the trapping stage. So the system wise is more robust. And one of the famous examples of this system is the nitrogen vacancy center in diamond. I'll explain more about the details about the NV centers. So this has been a already promising platform. Has been over a decade. People have investigated the practicality of this system. Has a long spin coherence time, up to like milliseconds spin relaxation time, even at the room temperature. And spin dephasing time also lasts around like few hundred microseconds at room temperature. So it's ideal for doing the quantum sensing, especially because now you need to operate the qubits in the room temperature for sensing. Also, you can also do some spin to photon interconnection to connect these spins in the wrong range. So people are using these defect qubits for quantum communications as well. And also all these things can be combined with the some cutting edge nanofabrication technique to make some structures out of it. So you can make some cavities or some other structures to make more enhanced performance of the devices. So these are the good things about these defect system. So some milestone examples of the achievements for past 20 years, people have already demonstrated using the MV diamond to sense the magnetic field from the living cells, and also doing the thermometry of a living cell using the nano diamond. And also now, because these MV centers are the atomic scale sensors, now you can probe almost like single proton level of NMR signal. So this allows us to have a very small scale, nanoscale NMR. So this really boosted and dragged a lot of attention in the field of nanoscale NMR. Now you can have a very tiny amount of samples to do high resolution NMRs. So you can make the giant NMR magnet to be very tiny, small setup with the diamond. So it has been very promising in the quantum sensing regime. And also in general, in quantum information regime, people have demonstrated that using these defects as a quantum memory, you can last these memory up to like few seconds. And now the world records is almost like hours and hours of memory time. And also, you can make these qubits and then combine them and make it as a fault-tolerant logical qubit. So this has already demonstrated in Netherlands, Delft group at the Netherlands. So it showed some promising route towards the realizing some logical qubit encoding for quantum information processing. So it is a very exciting system, relatively simple and robust setup compared to other atom trap experiments. So today I'll talk about seeing some of the introduction of the defect qubits and how we can make some a scalable platform using the defect qubits. And from that, I'll explain some applications of the platform towards the quantum metrology. So towards the multi-qubit, using the multi-qubit to have towards the quantum enhanced metrology. And lastly, some of our recent result on some quantum information processing using the MV centers in Diamond. So let me start with the introduction of the defect qubits in general. So there are lots of requirements to make the solid state spin defects to be a good qubit. And we can categorize into three main categories. One is the charge state. So these defects are generated within the solid state material. So if we want to make some encode the quantum information to these defect qubits, it has to be stable in terms of charge state. So we do a lot of manipulation by illuminating lasers or injecting like microwave fields. So during this process, the charge state of these defects should be stable, which means that the defect energy level should be securely positioned within the band gap of this material. So that's why we need to have a host material which has a wide band gap. So wide band gap is a preferred. So there are lots of candidates for the wide band gap material, like silicon carbide is a good candidate. So diamond is actually very wide band gap. It's like almost like a 5.5 EV. So that's why we use diamond for the host material. So it has to be charge state stable. And also, if we want to read out the spin state of the qubit, then you need to have some special energy level that's called optical intersystem cycling. So I'll explain later more about these details, but this kind of energy level is preferred. And also lastly, we encode information into the spin state of these defects. So we need to have a long spin coherence time to store the memory of the information. The longer the spin relaxation or dephasing time, it's better. So these three are the criteria for having the good defect qubits. So there are lots of solid state materials and lots of different defects that you can create. So people already investigated different class of materials and different defects, and they calculated what defects are most promising. So there are lots of examples. The famous example of MV diamond here has a emission wavelength of 600 nanometer. Some of the defects are in the telecom band, for example, like some oxide material and erbium doped oxide material has a 1500 nanometer. So it's already in telecom emission, so it's very useful for quantum communication application. But as you can see, depending on which material and which defect, the emission wavelength is all different. And also the operation the temperatures are all different. So MV diamond are the so far the best defect operating in the room temperature. But if you go to the low temperature, the tin vacancies or silicon vacancies are very promising because they have a very narrow line width, optical line width. So they are very useful for the quantum communications. So of course, you can also calculate the expected coherence time, T2, like T2 star, and you can kind of already speculate what's going to be the spin coherence time. So out of these different host materials and different defects, now people investigated different materials and different defects. And the goal is to find the best performing defects in different materials. So there are still lots of other candidates out there. Like 2D materials are recently gaining a lot of attention because it has also very interesting properties. So all these things can be investigated. So how do we control these defects? So there are different modalities that we can use. So One way is to use the optical control. So you can make these defects within the optical cavities. So this is a famous example of using the photonic crystal cavity. Now you can make these defects coupled to these cavities. And this allows us to filter out the unwanted optical bands, side bands, but only focusing on the wavelength that we want to filter. So some of the important informations are encoded into certain range of wavelength. So we want to filter that out. So that's why we use this cavity to enhance the useful photonic extraction. So that's how we actually do the optical integration. And also you can control these defects mechanically by using some strain. So you can make these defects into the cantilever structure to apply the strain, and this changes the spin-orbit coupling, and then that also changes the energy level. So you can tune the emission of the emission wavelength by tuning the strains of this system. And these can also be done by using applying the electric field by via the DC Stark shift. So electrically and mechanically, you can control these spins. And also, the most commonly used way is to magnetic field control. So by applying the AC magnetic field, you can actually induce the Rabi oscillation of this spin state. And this is how we actually generate the gate sequences for the spin qubits. So out of all these general explanations, so the most famous example is the nitrogen vacancy center in diamond. So MV center is basically consists of the substitutional nitrogen instead of the carbons. And also you need to have a vacancy right next to it. And this form the MV center. And how we make this is we first do the ion implantation and make the substitutional nitrogens into the diamond. And then we shoot the electron, we do the electron irradiation to generate the vacancies. And now we anneal the diamond. And by annealing, this allows the vacancies to be mobilized. And this actually migrates near to the nitrogen. So this forms the MV center. And then to use it as a useful qubit state, the charge state of the MV should be MV minus state. So you need a donor electron. So we get the donor electron from the nearby other substitutional nitrogen. And this forms as MV minus, and MV minus is an electronic spin 1 state. So it is not a 1/2, it's an electron spin 1 system. So the good thing, can be operated in room temperature, also atmospheric pressure, and also simply you can spin initialization can be done by illuminating the 532 nanometer laser, and also you can read out the spin state by also using the 532 nanometer laser. Spin state control can be done by using the microwave field signal. So I'll explain more about how we do this in the later slides. So now we have MV center in diamond, and how do we make this more scalable system? So imagine you have MVs here, and they're also nearby the carbon-13 nuclear spins, because the diamond itself, the natural isotopic abundance of the carbon-13 is about 1.1%. So you can easily find MV that are hyperfine coupled to the carbon-13 nuclear spin. So carbon-13s have nuclear spin of 1/2, so it's perfect qubit. So we use these carbon-13 nearby nuclear spins for physical or memory qubits. And by using the hyperfine interaction, we can make some useful gate sequences to control the carbon-13, to initialize carbon-13s, or read out the carbon-13 nuclear spin state. You can also make the multiple MV centers that are nearby. So when the MV centers are close enough, when I say close enough, is roughly like 10 nanometer closer than 10 nanometer, then these are in the regime of a strong interaction where you have a magnetic dipole-dipole interaction. So this allows us to use the connection between the MV centers to do some useful gate sequence, 2-qubit gate sequence between these two electron spins. So I'll also explain more how we do this in the later slides. So there are two different species. One is electron spin, the other one is nuclear spin. So we use this hybrid structure where we use both electron spin and nuclear spin. And electron spins are good for making very fast qubit gates because the electron spin has a very high magnetic moment. So it responds faster to the external magnetic field. And also these electronic spins can be uh, engineered and made into the very precise position where the nuclear spins cannot be controlled. So the position of the nuclear spin cannot be controlled. So we use electronic spin to make more scalable structure as a making some qubit spin register. But the good thing about the nuclear spin is that the nuclear spin has a very long spin coherence time because the magnetic moment is 1,000 times smaller than the electronic spin. And also these nuclear spins can be very finely controlled using the MV center hyperfine interaction. So by combining these good things of electron spin and nuclear spins, now you can realize more of a scalable hybrid platform. So the defect qubits are one of the platform that inherit the basic idea of NMR-based quantum machine. So we use a lot of techniques that already has been developed from the NMR quantum machines, but some of the limitations that was limited in the NMR machine can be resolved by having more of a scalable platform where we can make these defects into the desirable position. And also these quantum gates are done much higher fidelity and fast gate control using the electronic spins. And also by making these material more clean, more pure, now you can have less error into the quantum during the quantum operation. So this really enhanced the performance of the that was limited in the NMR machine, and now this spin defect quantum machine is showing very amazing performances. So this is kind of an overview. Yes, if you have a question.
Yeah, Paul, I would like to ask a question. Can you deterministically choose the position depending on the physical memory qubits? For example, you scanned the positions, random positions of physical qubits, and then you choose the specific point inside your crystal to do.
Yes,
Okay.
exactly. So let's say you have MVs and then you have a memory qubits nearby. Then we spectroscopically first determine how many are there and how strongly they're coupled. And by knowing that hyperfine interaction strength, now we can design a pulse sequence to selectively control each carbon-13s and not cross-talking to the other carbon-13s. So these kind of very precise gate designing has been already established technique. So it's adopting it's adopting the NMR based techniques.
Right. Thank you.
Okay. So this is kind of an overview of what I just mentioned. So we have a diamond chip, and now we have several MV centers in a desirable position, and we have several nuclear spins nearby. And now we want to interconnect these electron spins from the dipolar interaction. So there are lots of techniques to make this precise positioning of these MV centers, which I'll explain briefly how we did it in our lab. So using the ion mask implantation technique, but this is kind of overview. And then these carbon-13s, as I mentioned, we cannot precisely control the position of it because it just naturally happens. But we can spectroscopically analyze the precise position and precise coupling strength. So now we can selectively control with a very high fidelity. So this is the very common picture, not just limited into the diamond system, but also in other solid state platforms, they all use the same similar strategy. So people believe that having this single node, people believe that we can achieve up to 50 qubits of this scalable platform. And people are trying to have 50 qubits per node and interconnect these 50 qubit nodes via spin photon interconnection. So that's the strategy to make a more larger qubits in solid state systems. So let me just briefly explain how we do the control and readout in the system. So let's say you have MV centers, we illuminate with the lasers with the 532. So here's the energy level diagram. So this is the within the band gap of diamond. And this has the ground state, triplet ground state, and excited state. And because of the spin one system, it has a spin-spin interaction term, which is called, it's a D, expressed as a D. And this induces a splitting between the ms equals 0 to ms equals plus minus 1. And D determines the almost the resonance frequency of this MV. So it's in the range of a few gigahertz. So similar to the superconducting qubits. And as you can see here, there is a singlet state, which is a metastable. So how we initialize the spin state by illuminating 532 is the following. So when the spin is prepared in ms equals 0, then the green laser excites to the spin state to the excited state, and then it just decays, radiatively decay down back to the ms equals 0. But when the spin state is prepared in ms equals plus minus 1, what happens is that there's a leaking channel to the non-radiative decaying to the singlet metastable singlet state. So some population directly radiatively decays down to the plus minus 1, but the other population leaks to the singlet state. And then once it is leaked to singlet state, now the population now decays 50-50 to either ms is equal to 0 and ms equal to plus minus 1. So when you pump this population sequentially, what happens is that eventually the population is now leaked down to the ms equals 0. So this is how we actually initialize the in MV center. So you just continuously illuminate the 532. Then because of the leaking channel in the signal state, now all the spin state is initialized to ms equals 0. And this also allows us to measure the spin state because of the leaking channel is non-radiative, which means that there is no photon coming out from this path. So what happens is that when the spin is prepared in 0, then there are more photon coming out. And when ms equal to plus minus 1, then there are less photon coming out. So by reading out the number of photons, you can distinguish between the spin state of ms equals 0 and ms equal plus minus 1. So this is how we actually do the readout. And ms equal plus minus 1 are degenerate when you don't have any biased magnetic field. But when you apply the magnetic field that's aligned to the MV center's quantization axis, then you can induce the Zeeman splitting, and now you can address each energy level with the microwave field. So we can scan the microwave field frequency and then see the response of the optical photon collection. And now you can see some dip, and this dip corresponds to the each transition from 0 to plus 1 to 0 to minus 1. And this MV center can have different crystalline axes depending on which axis the vacancy is located respect to the nitrogen substitutional nitrogen. So you can have 4 different axes. So depending on different axes and projection of the magnetic field, now you can resolve all these axes in the spectrum, optical spectrum. So because of the Zeeman splitting, now you can have the transition by applying the microwave, like I mentioned. And now you can have, it is a spin 1 system, so it's not a spin qubit, but it's a spin Q-tree system. And by applying the resonant microwave field, transitioning from 0 to minus 1 or 0 to plus 1, you can induce the Rabi oscillation between these two sublevels. So this is one of the example where we induce the transition from 0 to minus 1. You can see a nice Rabi oscillation. And by choosing the microwave duration accordingly, you can make the Hadamard gate or pi pulse gate. So this is how we make the single qubit gate. And the resonance frequency is in the similar range of superconducting qubits. So we use a similar instrument as people use in the superconducting qubits. So this is the overview of the setup. So it's relatively simple compared to atom trap experiment. We need to have some pulsed laser. So we chop the laser using the AOMs. So we use AOM to make some pulsed laser. And we have microwave instruments using the AWGs or some signal generators to make the microwave signals with the microwave switches. And diamond chip is loaded onto the PCB chip with some fabricated microwave antennas. And we put it into the 3-axis piezo controller stage so that we can keep track of the focus. We have an objective lens to focus the laser beam onto the MV center. And because of the mechanical drift, we need to have some 3-axis precise control of the position. So everything is all synchronized, and we control everything via the FPGA control. And we have to synchronize with the laser and microwave and mechanical position. So this is kind of a very standard home-built confocal microscopy setup for MV or solid-state platforms. So next, I'll explain about, so using this platform, what do we do for quantum metrology? So quantum metrology is all about extracting the parameters from the measurement. So you have a quantum system, you have a prepared quantum state, and now this quantum state interacts with some signal from external signal. So it evolves into the different quantum state. And now we measure the final quantum state and extract the parameter from the final evolved quantum state. So the precision of extracting this quantum parameter is determined by the so-called quantum Fisher information. So probably you've already heard about the quantum Fisher information. So it is bounded to the quantum Fisher information, but what we measure in the system is in fact the classical Fisher information. So we have to design the measurement system that's approaching to the quantum Fisher information. And this requires the designing of what kind of a measurement that we have to do, like how we design the POVM or how we do the measurement basis in the quantum measurements. So this is kind of a very basic idea of how we do the quantum parameter estimation. So usually we measure the phase information in the block sphere where the block vector evolves, and we just measure the change in the block vector phase. So this is a very famous example. It's called the Ramsey interferometry. So we first prepare our qubit, in this case, the MV center. Now we apply the pi/2 pulse. This is similar to Hadamard gate. So you prepare into the superpotential state, and now you let it evolve and interact with the external signal. So from that, the spin qubit acquires some phase. And then now we want to measure this change in phase to extract the signal information. So to do that, we need to bring it back to the population state to read out. So we apply additional pi/2 at the end, and then now we just measure the spin population. And this allows this. So when the signal kind of evolves into this XY plane, what we actually observe is the oscillation signal. So basically, this projection measurement, by evolving this phase, now you observe some oscillatory signal. So this is how, and then the optimal POVM in this case can be designed to the projection to the plus and minus basis, where the plus is the superposition between 0 and 1. So usually people interpret the quantum Fisher information in the phase parameter space. So in phase parameter axis, the quantum Fisher information is maximum quantum Fisher information is just 1 in Ramsey measurement using the single qubit. But in terms of, so in the spin sensors, we normally, what we measure is the external magnetic field signal or some other physical signals rather than the just phase information. So to convert the phase information to the signal information, we have to adopt the measurement time into the quantum Fisher information picture. So this makes the quantum Fisher information to be dependent on the sensing time squared. So if you just plot it, then it becomes a quadratic function. So it is a very different, looks very different from the different perspective of measurement, where if you just measure the phase, then it just doesn't change in the phase parameter. But in terms of the signal sensing, the measurement time becomes very important. So in practical quantum sensing scenarios, we normally want to extract the magnetic field signal. So the right-hand side of the figure is more applicable. So using these spin qubits, how can we actually do true quantum enhanced measurement? So to do that, we need to push the quantum feature information to the farthest limit, because the measurement sensitivity is normally bounded by the quantum feature information. So to beat the standard quantum limit, we cannot just use we cannot use the just classical states. We need to use some quantum mechanical non-classical states. So famous examples are entangled state or squeeze states. So many of you already know about these basic ideas. So famous example of using the GHZ state, which is the maximally entangled state of n qubits. Now you can see the signal. When you have a single qubit, the signal oscillation, the modulation frequency is quite slow. But if you have n number of qubits that are all entangled, then as you can see, the modulation frequency becomes faster, and the sensitivity, which is a performance of the qubit sensor, it depends on the maximum slope that you can get from this signal. So as you have a faster modulation, the maximum slope that you can achieve becomes larger compared to the single qubit case. So this really allows us to have beating the standard quantum limit. So this requires entanglement, and entanglement is a very important resource, especially also in the quantum sensing perspective, not just quantum computing. So using these spin defects, how can we actually achieve this entangled state? So that's a very important topic in the field. So to do that, people have investigated using the electronic spin interactions to generate the entanglement. So people already have shown that there are very interesting quantum many-body phenomena happening in the dense spin ensembles, where you have a very dense MV centers that are spin dipole-dipole interacting. Then people have already shown that you can have some interesting quantum simulations, for example, like discrete time crystal phenomena, or using these spin-spin interactions to simulate some hydrodynamic many-body effect. And also people have proposed to use these electronic spin interconnections to make some spin network for scalable quantum modules. So basically, we want to have some entanglement, and the resource for the entanglement is basically spin-spin interaction in the system. So it's a very, it requires a strongly interacting spin system. So people made these kind of devices based on the MV centers, and people have used the MV. So basically, you make a very dense ensembles of MVs in this diamond system, and you induce very strong couplings. And using these strong couplings, people already demonstrated now you can make some spin squeeze state in diamond. So this already has been recently published in Nature. So they generated the spin squeeze state in a dipole interacting system. And also not just the electrons MV-MV interactions, people already use the MV center and the nuclear spin state and generate the entanglement to show some quantum enhancement in quantum metrology. And there are also proposals to how to make these entanglement more efficiently within these electron-electron interacting systems. But people have numerically simulated what's the most efficient way of in circuit structure, how to generate these. That has been already proposed in the theory side. So the goal is to make some small scale local MV centers or nuclear spins that are highly entangled. And this entanglement can be a very important resource to achieve higher quantum feature information for quantum metrology. So for example, let's say you have two MVs that are close enough so that they interact strongly beyond the decoherence timescale. So that's the requirement. So you need to have a strong interaction so that you can see this interaction within the spin coherence time. So to induce this entanglement, the entangling gate is very simple. So when you have two MV centers, the Hamiltonian for the interaction can be interpreted as the spin SZ-SC interaction. So spin Ising term is basically the dipole interaction Hamiltonian. And by using this Hamiltonian, you let them interact. And by tuning the time of this interaction, now you can make the maximally entangled state. And this is called the Bell state. So you first prepare these two MVs into the superposition state, and you let them interact, and you evolve certain amount of time. And now you finally, by carefully choosing this evolution time, you can generate the maximally entangled state. So this is a basic picture of how we generate the entangled state between electronic spins using the dipolar interaction. So beyond this just 2-qubit example, I want to explain how people are trying to realize these entangled state in ensembles. So it sounds simple, but in fact, there are lots of technical challenges. So one of the challenges is that these electronic spins are positioned within the diamond sample, but their positions are all random. So which means that the interactions are all also random. So the randomness of the interaction becomes a big problem, because if you want to do some coherent operation to induce the large scale entanglement, you need to have some homogeneous interaction. So this randomness interaction is a problem. And also another problem is that the interactions is always turned on. You cannot turn on and off this interaction because these spins are always interacting together. So there are lots of crosstalks happening between multiple electronic spins during this operation. So these are the very big challenges of realizing the small scale entangled system in diamond. So we kind of developed some tools to mitigate this issue by using the technique called the double dressed state scheme. So I'll explain about this scheme later. And we deploy this scheme to the example of two strongly interacting MV centers and see how that works in this system. So basic idea is the following. So MV centers are spin one system. So we inject the microwave signal to two different transitions from 0 to -1 and 0 to +1. So you inject two different dressing field of microwaves. And by tuning the relative Rabi frequency of these two transitions, we learn that the effective dipolar coupling between these two MVs can be tuned by tuning these relative Rabi frequencies. So it's a very simple idea. So you just have two different fields with the different field strengths. By tuning these field strengths, now you can effectively tune the dipolar coupling. So that's the basic idea. So you have two MVs that are less than 10 nanometers. So you can individually control them because their resonance frequencies are quite different. So you can individually control them. And you can also detect the coupling strength between these two MVs by using the double electron resonance measurement. So from this measurement, it's basically you're using one of the MVs as a sensor, and you're sensing the field generated by the other MVs. So that's the basic idea. So by doing this spectroscopy, you can measure the bare dipolar coupling strength. So that was around like 0.25 megahertz in our case. So you can spectroscopically also measure this dipolar coupling strength using the Ramsey pulse sequence. So Ramsey is a very good spectroscopic way to detect the magnetic fields. So by changing the basis of how you do the measurement of your sensor of MVA, so MVA is used as a sensor spin. So by changing of different bases, you can see the different response of the MV phase accumulation. So I'm not going to go into the details about this measurement, but basically you can deploy Ramsey measurement to detect the dipolar couplings. So that's the basic idea. And now we use this double dressed scheme onto the Ramsey measurement. And here we wanted to see how the effective dipolar coupling actually changes by tuning the relative Rabi frequencies for different transitions. So by changing the omega-1 and omega-2, and by varying these numbers, we've observed that the effective coupling strength kind of can be tuned almost continuously, and also almost goes to zero. When you have omega-2 and omega-2 are the same, then this effectively turns off the dipolar coupling between these two MVs. So we've shown that you can continuously tune this, and this show that now the effective coupling between the MV spins can be deterministically controlled by injecting these microwave fields. So why this is useful? So we've demonstrated for the two MVs. Now we simulated by having the multiple MVs, so ensembles of MVs with the random positions. So this it's kind of Monte Carlo simulation where you have random interactions between these spins. So if you don't have any drivings, or if you just let it interact each other, then the distribution of this interaction is very broad, which means that the system is very inhomogeneous. But by applying this double dress scheme, what we could achieve was to narrowing down this distribution of interactions. So it kind of makes the interaction more uniform. So this is useful for, especially for when you want to generate the large scale entanglement within this random spin ensembles. So we kind of simulated and then confirmed that this kind of a double dressing scheme makes this inhomogeneous system more homogeneous. And of course, the overall mean interaction strength becomes becomes smaller than the non-dress state, but still the interaction, the distribution becomes much narrower. So we believe that this can be very useful for generating the large-scale entanglement in the very random system. So another aspect of this system is, as I mentioned, these systems are random, so MVs are generated in the random position. But in terms of the device side, now people are investigating whether we can make the position of these MV centers in a very precise, deterministic, precise position. So this allows us to have more uniform interaction. So even though the positions are still quite random, we want to make these devices as uniform as possible. So we developed a way to do that by using the mask implantation technique, so which has been already used for over 10 years. People make very tiny hole on the surface of a diamond, and then now you implant the ions that's passing through these tiny holes. So your MV centers are generated within that range of this tiny hole. So that's the idea of making this very confined position of the MV centers. So we'd like to make the precision of this MV center generation, the precision to be less than 10 nanometers. So that was our goal. So to make these devices, we first make some very tiny hole structure using the nanopore structure. So we make some thin layer of a silicon aluminum alloy, and when you apply some when you anneal this to high temperature, there becomes the phase separation. So because of the phase separation, now this aluminum becomes in a very uniform nanoporous structure. And just selectively etching the aluminum, now you can generate the silicon mask where you only have a very uniform nanopores and silicon mask. And having the secondary mask layer on top of this nanopore structure, now you can confine this small number of nanopore structure. And this makes as a mask when you do the E-beam, when you do the ion implantation. And this makes the confinement that's as small as the size of this nanopore structure. So this is the device image. So we made small, tiny structure where the average nanopore diameter was around 6 nanometer. and it was relatively ordered in a structure. And we made a secondary mask, and then we did the ion implantation of the nitrogen, and then we made the epicenter. And as you can see, they're like a grid in a grid structure. And within this little grid, one single spot, we generated up to single to 3 MVs. So these MVs are positioned very close to each other. So we spectroscopically just measured how many MVs that we generated per spot from the G2 autocorrelation measurement, and also from the ODMR measurement. We kind of confirmed that now we make small clusters that are positioned very close to each other within the single spot. So this kind of a direction that we want to make some scalable electron spin, high precision in the positioning of these defects. So switching gears, so having these MVs, generating many MVs, which sounds very nice, but because these solid state materials are very, very noisy environment. When I say noisy, what I mean by that is that you just want to make the MV centers, but while you make the MV centers, you inevitably generate the other types of defects as well. As you can see here, there are lots of different defects that you generate. So MV minus is one of the target defect that you want to generate, but they're also just vacancy centers, which is not combined with the nitrogen substitutional defect. So they're vacancy center. Also, they also carry these spins. So these are also some small magnets generating noise nearby the MV minus. Also, some other complex defect complex like MVH minus or VH minus, or even substitutional nitrogen that's not generated to MV center, which we call as a P1. So all these different defects that are remaining within the diamond are acting as the source of noise. So these are just oscillating, these are generating oscillating magnetic field noise. So this limits the coherence time of the MV center. So this becomes very critical when you make the large scale entangled state. So entangled states are more sensitive to the fluctuating magnetic field, which means that it's more fragile, and the entangled state lifetime is limited by the highly highly affected by the noise environment. So some people say that even if you make the entangled state, it's not very useful because the coherence time is much shorter than the single spins. So now the question now goes back to okay, so now we are limited by this dephasing. So we cannot have such a large entangled state for useful quantum metrology. So we only have few defect spins. So how can you do a better job using the very few numbers of spins in this diamond platform? So that brings us to the next topic of post-Alexa metrology. Summary. So I've shown that the MV center, basics about the MV center, and some routes to achieve the quantum enhanced sensing. And I've also talked about some of the challenges about large-scale spin entanglement, some of the device aspect, how we can tackle down this problem, and some control techniques of a double dress control schemes. And also, achieving large-scale entanglement still is technically very challenging. So having just small-scale spins with the dephasing noise, how can you do a better job? And I introduced some of the recent work on the post-selection metrology. So hopefully I delivered the message here. And here's an acknowledgement. And thank you for listening.
Thank you very much, Paul, for beautiful results and wonderful talk. So we would like then to ask a few questions, if you allow.
Yeah.
So please, audience, if you have. So please, Sergei Shevchenko.